Alright guys, so let's talk about vertical circles today. So as I was mentioning before, all that we've done so far is horizontal circles, so that they're moving parallel to the surface. This lesson is about vertical circles, so when we think about those, it's like roller coasters and stuff like that. So yeah, like roller coasters would be a vertical circle because you go upside down. So anything that goes upside down is a vertical circle. So let's think about this logically, all right? So we know that we have centripetal force is the force that goes to the center of the circle, right? That's what we kind of concluded yesterday. Notice though, there's one question that I had yesterday regarding just the theory of this. Just that I thought I'd clarify. So if we have circular motion, we have centripetal force moving in toward the circle. But when we think about like what we experience in a circular motion is that we kind of feel we feel pushed to the outside, right? That's our centrifugal force, which actually isn't a real force. It's a resultant reaction from this force. So for every force there is an equal and opposite reaction. So centrifugal is like what you feel when you're in that circular motion. Or when you're twisting something overhead, right, if you let it go, it goes off in a direction, right? That's centrifugal force. Centripetal force is what we focus on, is the actual pull of the object toward the center. Or the centripetal force that it's like it's pulling it toward the center, but the velocity is actually, it changes every time. It's kind of a hard concept. But I'm just focusing on centripetal force. So it's always moving towards the center of the circle. So I just wanted to make sure we are all, okay, centripetal, center. All right, so I have this bucket of water. If I made a vertical circle with this, would it dump on my head? So if I went around, did a vertical circle, would it dump on my head? No. What circumstance would it not? If I go fast enough, okay? So I need a certain speed in order to counteract the gravity, right? Because if I dump this water, if I turn this bucket upside down, there's the force of gravity, and it pulls it down. But if I develop enough speed to develop a strong enough centripetal force, it will keep the water in the bucket. Okay? So, let's try it. I'm going to move away from my smartboard. Don't psych me out or anything. Okay, so I'm going to do it fast. There's a fair amount of water in it. Oh, I'm pretty good, eh? Who else wants to try? Yeah, if the handle doesn't break. So that's a good point. I need strong enough tension in my handle in order to take all of the centripetal force. Okay? And I need that to be stronger than gravity.
Did Mr. Craig do that?
Okay, well, this is my class.
He had a board on the water on the board. Cup went flying off.
Who else wants to do it? It's fun. Reed does. No? Nobody wants to do it? It's fun. Okay, I'll do it again because I think it's fun. Woohoo! Think I should go slower?
No, because you're going to spray up.
Woohoo! Whoa, that was close! Okay. Alright, so that's what this says. Let's consider a mass whirled in a vertical circle at the end of a string. So the string would be like my arm. I would be the center of the circle. Okay, my shoulder would be the center. And here's like the string. So this, my arm would be the radius, right? Okay. So if we were to kind of draw this, when the bucket's at the very top, we have tension, right? As Matt said, there's tension. So the tension, so if this is like my shoulder, the tension is coming down. I'm holding the bucket, and so there's that tension between, this would be the bucket or the mass, and my shoulder. But then we also have the force of gravity. So, and let's make a note here, Fg is same direction and magnitude everywhere on the circle. So no matter whether it's on the top, the side, or the bottom, our Fg will stay the same because it's due to gravitational pull. All right, so now if I was to think about the centripetal force here, I can say that my Fc is equal to Ft plus Fg. The force of my tension and my gravity need to equal my Fc in order for that to be over top of my head and not be falling on me. Okay? Now, anything that goes toward the center of the circle, so any force that is toward center's circle is positive. Anything that is moving away from the center of the circle would be negative. So it doesn't matter where it is pointing, as long as it's pointing into the circle, it's positive, pointing out negative. So that's why I could set Ft here to positive, because it's going toward the center, and Fg is also going toward the center. Here though, I'm at the bottom, so this would be like when my bucket is just hanging down, okay? So now, if it's just hanging down, and here's my shoulder, pointing up now is my Ft, because I'm holding it. That's where the tension is, okay? And Fg is still going down. But now Fg is not going toward the center of the circle, because the object is now at the bottom. So now I set Fc is equal to Ft minus Fg. Now, this concept is just a little bit new and things, so I want you to write down page 261 and 263. Give good explanations about this concept if you want just a little bit of review or a different kind of perspective on it. Okay, next I want to, oh, you guys have this next one. So, for vertical circle problems, this is your next part there. For vertical circle problems, to calculate minimum speed at the top of the circle, so the object doesn't leave, so falling, the tension needs to be, well, we set it to 0. This is true for maximum radius questions also, because this is looking just for minimum. So we say, I'm just going to explain why. So you are seeing how much force is needed to equal / or overcome gravity so that it doesn't fall. So this is specifically when you're looking at minimum speed questions, if it asks you about minimum speed, or maximum radius. So you use object at top, and ft is equal to 0. So then, when you do that, I'm just going to erase this part. When you do that, your formula changes as so. So if I have FC is equal to FT plus FG, now my FT, I can set that to 0. So now I have FC, which I can, if I'm given speed and radius, I can substitute this for v squared over r. Which is equal to, I know my FG is m times g. Oh, sorry. I'm going to just back up one step here. I should have done something different. I'm just going to set FC equals to m times AC, because AC could be two different options. And this is equal to m times g. So if you did set your AC to v squared over r, you can also here cross out m's because they're both on the same side. Now I have v squared over r is equal to g. So this is one of the skills in just kind of rearranging formula for this type of example. I'm going to show you more. But basically you can take what you know about FC and FG and substitute them into this formula and simplify it. Okay? So this is a summarized formula. So it's not on data sheet. You need to know how to do this.
What does G represent?
Gravity, like 9.81 meters per second squared. Because that comes from our mg. Yeah. Okay, now I want you to flip over your sheet so that you're on the back of your page and there's a blank sheet. Blank, go to the blank side. Yeah.